This photorealistic 3D tree is being dynamically relit in real time, but this calculation isn't taking place inside a 3D engine. It is occurring entirely within a flat 2D compositing workspace. Modern VFX workflows allow compositors to adjust 3D lighting in post-production. This bypasses the immense computational cost and time required to re-render the original 3D scene for every minor artistic change. The tool that enables this is the Normal Pass. It appears in a compositor's node graph as a flat, brightly colored neon image sequence. This creates a mathematical paradox. Calculating 3D lighting falloff and physical shadows requires spatial volume, which is seemingly impossible to extract from a two-dimensional image. The secret lies in the data structure of the RGB channels. In a Normal Pass, color values are actually encoded spatial coordinates, where red is the x-axis for side-to-side orientation, green is the y-axis for top-to-bottom, and blue is the z-axis for depth. Relighting a 2D image is not a software trick. It is the isolated mathematical execution of the physics of light, using color data as a proxy for geometry. To understand how this data is used, we have to look at the rendering equation. The rendering equation is a formal integral that expresses the balance of light energy leaving a surface point as the sum of its own emission and the reflection of all incoming light. This calculates radiance reflecting off a surface toward the viewer. Solving it requires integrating all incident light across the hemisphere above a point. The critical variable is the Lambert factor dot product, returning the angle's cosine between two vectors. The Lambert factor dictates that light weakens as the angle of incidence becomes more glancing. This angle establishes the surface normal vector as the primary geometric input for calculating any physical reflection. Lambert's law shows that a perpendicular light bundle delivers highly concentrated energy to a surface. Striking at an angle spreads the energy, reducing brightness. The dot product between the incoming light vector and the surface normal provides the exact numerical value for this energy falloff. However, true mathematical curves do not exist in standard rendering. Most 3D surfaces are constructed from a mesh of flat polygonal triangles. If lighting is calculated using the true geometric normal of each flat polygon, the rendered object will appear visibly jagged and faceted. Render engines solve this using per-pixel shading. The engine averages the normals of adjacent flat faces to generate artificial, smoothed normal vectors located precisely at the vertices. These vertex normals are mathematically interpolated across the surface of the triangle, creating the illusion of a smooth, continuous gradient. Without disinterpolation, discrete triangles cannot simulate a continuous surface, making the vertex normal the primary data structure for visual smoothness. This interpolation rule fails when a 3D model is intended to have a sharp, faceted geometric edge, like the corner of a metal box. If the engine averages normals across a 90-degree corner, the lighting begins bleeding across the edges. This creates a bloated shading artifact that makes a hard cube look like a soft balloon. Preserving the edge completely requires topological detachment. It's a modeling procedure where shared vertices between polygons are duplicated and separated to create sharp discontinuities in the surface data. By physically slicing the intersecting faces of these hard edges apart, 3D artists completely sever the shared vertex data. This forces the engine to calculate separate, independent perpendicular normal vectors for every intersecting side. Because the vertices are no longer shared, the interpolation algorithm stops at the edge, perfectly preserving the hard lighting discontinuity. Managing surface normals is therefore a balancing act between forcing artificial smoothness and protecting rigid mathematical boundaries. The final hazard in the pipeline is the transformation of vectors from local object space to world space. Position and velocity coordinates are contravariant vectors. These are spatial quantities that scale in direct proportion to the transformation of the coordinate system. Surface normals, however, are called covariant vectors. These are gradients that must scale in the opposite direction of the coordinate axes to maintain their 90-degree perpendicular relationship to a surface. If we apply a standard horizontal stretch to a circle, the normal vectors wrongly tilt with the stretch, losing their 90-degree alignment. The standard transform fails because the normals followed the horizontal scale instead of maintaining their relationship to the newly sloped surface. To prevent this, rendering engines must forbid the use of standard transformation matrices for normal data. The engine must instead apply an inverse transpose matrix, denoted as m to the negative t. The inverse transpose is the transpose of the inverse of a transformation matrix, which correctly orientates surface normals when an object is non-uniformly scaled. Finally, every vector must be renormalized to restore its mathematical length to exactly 1. A mathematically accurate normal vector is a complex data point that has survived interpolation, topological severing, and inverse transpose math. This math brings us back to the 2D compositing node graph. An RGB normal pass is essentially a baked snapshot of millions of these mathematically corrected covariant vectors. To relight the scene, the compositing software must first rebuild the spatial volume. First, the software uses a position pass to rapidly extrude every single 2D pixel into a 3D point cloud. A position pass is an image sequence where the RGB values of each pixel store the actual x, y, and z coordinates of that point in 3D world space. The artist then places a virtual point light source at a specific coordinate within this newly simulated space. The software calculates the trajectory from the virtual light to every single point in the cloud. These trajectories become the incident light vectors required by the rendering equation. The geometry of the scene has been successfully rebuilt without ever loading the original 3D mesh file.